Okay, and we are recording. I'm going to share screen.
The hardest part of the talk.
Yeah. And I got my head down there.
Oh, cool.
Oh, you're doing that thing again.
You hate this?
No, I love it. I just wish I knew how to do it.
When you go to share, you have to just hit advanced, and then it says use a PowerPoint as virtual background. Okay, so we're going to talk about network analysis today. So when people hear network analysis, the most common way you've heard about it is looking at social networks. So that's like looking at who's friends with whom on Facebook or Twitter, and things like that. Or on self-report measures, having people list their closest acquaintances to look at sort of social network overlap between companies or things like that. That's a little different type of social network analysis. And there are, I mean, your sample, each person in your sample is a node, or in those kind of networks. The networks I'm talking about today are psychological networks. Those are inferred, and it's sort of an exploratory alternative to running some confirmatory SEM analyses. So the variables that you're looking at are called nodes when you're talking about network findings. And I'm sorry, my head's kind of in the way. I can make my head littler. And they're represented as circles. The links, but the unique associations between each pair of variables or each pair of nodes are called edges. When you graph them, the thickness of the edge is an indication of how strong that association is. And the color of it tells you whether it's a positive in blue or a negative association in red. And when you do, this is called a spring graph. When you do a spring graph, you're using this modified Futcherman-Reingold algorithm to put nodes that are more strongly linked to each other closer next to each other. And the idea is you can tell which processes are maybe more central or more connected to other processes by whether they are in the middle of the graph or on the periphery of the graph. Now, so people typically show network results with these spring graphs. You just have to take them with a grain of salt, because the exact position of nodes, of variables, in a graph like this is a little chaotic. Like if I were to take one or two paths and strengthen them just a tiny bit, probably not even enough to make much of a real world difference, this graph could completely tangle itself a different way. So people graph these, but you don't want to put too much faith into exactly how it gets graphed in these spring graphs. And by the way, there are different indices of centrality. Strength is just literally adding up the absolute values of the weights with other variables. So if a variable has stronger centrality, it just has bigger edges going to it. Closeness is how many really strong edges it shares with other things. And betweenness is how many other pairs of variables it acts like the most proximal mediator to. When you are doing network analysis in R, you have a number of packages you can choose from. BootNet is probably the easiest to use, and it's fairly comprehensive. So and by the way, I should give credit to Sasha Eskamp. It was his articles that helped teach me network analysis. That's one of the articles I gave for everybody to read was from him. Also, during the pandemic, he made his week-long workshop on network analysis freely available. They recorded the videos and left them up on the web for a year. So I downloaded and watched every minute of those. So this is mostly a brief translation of all of that material. So BootNet is the most comprehensive. It contains the QGraph package, although it seems like to use some of the things in QGraph, you have to load that package separately. Sasha has been working on one called Psychometrics, and it has some model searching functionality that the other ones don't. It also will eventually be able to run network analysis on latent variables, which is kind of cool. So Psychometrics is trying to sort of merge SEM a little more directly with network analysis. MGM is another package. It can use mixed data. So if you have continuous and categorical variables, it would probably be the most appropriate. It's also set up to look at time series data, which is handy. So if we have daily diary or weekly or monthly diary data, MGM might be the preferred package. You can also, a lot of what we're going to be looking at is just unique associations between variables, literally partial correlations. But in MGM, in addition to looking at the partial correlations, you can look at how different nodes interact with each other to predict other nodes. So you can add a term to say, look at all two-way interactions, look at all three-way interactions. Most importantly for today, I'm going to be showing you BootNet code, but we're going to use MGM to get multiple R-squared estimates so that we have a sense of how much variance in each node is being accounted for. And then there's the BGGM package, which allows for Bayesian estimation. So you can put in prior probabilities. So when we're talking about psychological networks, usually we are talking about partial correlations. And specifically, we're looking at how each variable in a set of nodes, each node in a set of nodes, is linked to each other variable, controlling for all of the other associations in there. So it's you take a correlation matrix and turn it into a partial correlation matrix. So these are also called Gaussian graphical models, and they happen to be a subset of Markov random fields. So sometimes in the literature, you can see it referred to as any of those names. One of the issues you have to worry about once you start looking at partial correlation networks is that you might get some spurious links. There could be, if you were doing it in a gigantic sample, you could get a bunch of near zero associations that come out as statistically significant, but don't really reflect much about what's going on in reality. You can also, you also have to deal with suppressor effects. If you have a lot of really collinear, strongly correlated variables that you're throwing in, then suppressor effects can come out, just like they can come out in regression. To reduce that concern, there are different strategies. If you're working in a smaller sample, you can use regularization, which is a thresholding technique to sort of screen out the smaller partial correlations and just focus on the ones that you have more faith in. In larger samples, instead of doing regularization, they recommend doing sort of model selection techniques. So I'm going to show you two of the main form of regularization people use and the main form of model selection that Sasha recommends. I'm calling him Sasha. I've never met him, so it's his first name's way easier to pronounce than his last name. So what is a big versus a small data set? So to take an extreme two extreme examples, if we have 2,800 subjects and only 25 variables, that's considered a big data set. The number of subjects far outweighs the number of nodes. And in his 2017 tutorial paper that I sent you, he argues that lasso regularization, pruning, and model selection all kind of converge to give nearly identical results. But actually, since in the 5 years since that was published, they've done more Monte Carlo studies, and they actually find that lasso, and I'm going to cover this in another slide, so I don't know why I'm pre-lecturing, but lasso regularization can actually cause more harm than good if you have a big data set. So if you have a nice big data set, then model selection is preferred over regularization. And within BootNet, there's this ggm mod select function that kind of combines the best strategies in an intelligent way that seems to reproduce, that functions well in Monte Carlo studies. If you have 500 subjects or less, and closer to 240 variables, obviously your number of variables is coming close to the size of your sample. Things like that are considered small data sets, in which case you probably shouldn't use model selection. You should use lasso regularization. That's where lasso regularization really works well. So the tutorial paper I sent you was specifically on doing network analysis in a smaller data set with lasso regularization. Now, this example I'm going to show you today in the second half of this is in a big data set. So I'm actually going to show you using model selection. Any questions so far? Everybody with me?
What does lasso stand for?
That is an awesome question. I have no idea what that acronym stands for. Do I have that paper pulled up?
No, it's okay. Forget it. Go on.
I don't remember. So this is an example. This is using regularization in a small versus a large data set, model selection, pruning, and two different types of pruning. And you can see in a small data set, in a large data set, the top row, when you have a lot of observations and a small number of variables, you do get really similar results regardless of which one you use, at least in this example. But in small data sets, which strategy you pick radically affects it. And that's why they recommend lasso regularization, which is done with the EBIC Glasso subroutine or function.
So Ron, you're kind of talking something with your head for the last slide. I was just curious, like, so you have the N down there and the number of variables. So oh, okay, you made yourself tiny. Is the problem there that it's the N, but it's also the number of variables? So like,
well, the problem there is you're using a pruning with Bonferroni is really only functions well in really big data sets. So you're getting you're wiping everything out because the strategy to simplify your network down to the most stable and reliable edges is not suited for the type of data you have here. Does that make sense?
So basically you can still do it in a sample like 500, but you just couldn't do it with 240 variables, which is kind of seems like an insane.
Well, you can do network analysis in a sample of 500 with 240 variables. This whole bottom row is that condition. It's just you should use lasso regularization if you're doing that kind of a network. So the point of this, oops, shit. I'm just going to share screen regular. Oh, the point of this screen, oh, this is what I want, is that this lower left-hand one is the optimum one, Like this would be a more interpretable solution. It would shed light on what was going on. So if you have 500 subjects and 240 variables, you should use lasso regularization.
Okay.
Does it make sense?
Mhm.
So what is a small sample? They say you should have 100 to 500 subjects. Well, if you have 100 to 500 subjects, that's a small sample. You should use lasso regularization. They say the more subjects you have, the more stable those partial correlations are going to be, the more you can trust those edge weights. So they would probably encourage you to have 500 or more, but you can publish. In fact, we just published, I helped edit a paper running network analysis in 120 undergrads, from somebody else's paper. But nobody had done that before. It was an interesting question. So we published it. They just needed to acknowledge that it was a small sample and their limitations. If you have more than 50 variables, then you may need closer to 700-800 subjects before it's no longer a small sample. Because as you add nodes, you're adding a lot of edges that you're having to estimate. A ton of extra partial correlations. Does that make sense? Okay. So lasso regularization is well suited if you have a lot of predictors and fewer subjects, so you're in that small sample zone, and you're anticipating a sparse model. The most current Monte Carlo findings actually suggest that in really large, robust samples, lasso regularization might not be necessary, and it could actually do more harm than good. So the tutorial I gave you was on lasso regularization, and they do a nice job of explaining it. And they explain the different parameters that you can set in lasso regularization. Although I'll tell you, when you go in to do it, the R functions do a lot of that adjusting for you. You don't even have to worry about that. If you have a big data set, the other alternative is model searching. So it's trying out various models to optimize fit. The simplest is set all edges to 0 and then use modification indices to see which edges are going to account for the greatest addition of covariance or explanation of covariance, and slowly add edges in until you reach a threshold. But there are more advanced ones. If you've added an edge, or if you add several edges and then some of the ones that were already there suddenly get weak, you can prune them out. So you can do sort of a step up in pruning. There's within psychometrics, there's a model search function that does an even more advanced algorithm. And even though Sasha is one of the lead programmers on psychometrics, currently he recommends the bootnet package's GGM mod select function. It seems to have the most effective strategy. Takes a bit to run, but it's effective. So this is in bootnet and QGraph. It's quite conservative. The Monte Carlo studies show it's highly likely to converge on a true model. And I'm not going to go into the strategy. The syntax for doing it is fairly easy. So why is it not letting me annotate? Because I'm in this weird mode. So the function is this estimate network. And then in the parentheses, we're giving it a data frame that has our data in it. You say stepwise equals default equals GG mod select, telling it which extraction to use. And we're gonna tell it Spearman correlations, and that's because that helps deal with the skew in your data. And then you arrow that into a new data frame, which can have any name, but this is where your results are going to live. Okay, so most multivariate analyses assume we have normal data, normal distributions in our data, and that we also have multivariate normality. Thankfully, the vast majority of them are robust to violations of that assumption. So running multiple regressions or HLM or even SEM, if you do it on untransformed data and on transformed data, you tend to get nearly identical path coefficients. So much so that journals don't even ask you to transform your data or report your skew anymore. Unfortunately, network analysis is a little more sensitive to violations of that assumption. And you can, I guess, the estimating partial correlations, controlling for 30 other variables, those can be really sensitive to skew. Skew can make things look a little more correlated. So the best thing you can do to deal with skew in your data, well, if you have item level data, this is especially problematic because you don't even really have interval data, and you definitely would have skew, or you most likely have skew. But when they were presenting this in the talks, it seemed like they were talking about this not just with item level data, but with any data. If you want to deal with skewed variables, the best thing you can do is non-paranormal transformation. And there's a huge package that lets you do that. Unfortunately, the huge you cannot have any missing data if you're going to use the huge package. The next best solution is to simply run Spearman correlations and estimate the partial correlation matrix based on a matrix of Spearman correlations. And that actually handles skew pretty well. In BootNet, it defaults to polychoric correlations, which are the most appropriate for ordinal data, the kind of data that you would get from items. Polychoric correlations do a fantastic job of handling skew, and but they really only do that well if you have samples of 1,000 people or more. It can be unstable and throw errors in smaller samples. If you have true false items, I would ask why do you have true false items, but then you have to do ISING models. And they don't know what advice to give people if they only have 3 or 4 answer choices. So you need to, and this is the start of some R code to transform something with a huge package. And I'm going to show you code later where you'll see me doing this in the data set. You'd pull in the huge library, and then you literally just run huge.npn for a non-paranormal transformation and give the data frame. Fortunately, in BootNet and Psychometrics and BGGM, you can, if in BootNet, if you use correlation method Spearman, that effectively deals with skew in your data. In Psychometrics, if you say ordered equals true, it does essentially treats it like ordinal data. And its type equals ordinal in BGGM. Okay, so that's a background. Ooh, and we're halfway. That's a background on most of this stuff about network analysis. So now I'm going to show you a paper that my first paper that I used network analysis on. I wanted to test this model, looking at tenets of Buddhism and how they shape mindful lenses that we view the world with, how we flexibly or inflexibly respond to aversive stimuli, how that shapes our value-driven behavior, and how that impacts individual function. So this model, I had already published a paper on this unified flexibility and mindfulness model proposing these 3 stages. I had just published a paper on the 3 teachings of East Asia scale. So we're using the Buddhism subscales from that. And we are linking this model to forms of mindfulness discussed in Buddhist teachings. We have cross-sectional data from about 2,000 people from both the United States, China, Japan, and Taiwan. So we had the entire survey translated into simplified Mandarin, traditional Mandarin, Japanese, and Japanese, those 3. We had initially planned on running structural equation model analyses to test that model that I just showed you, that we had already published a paper on. So it would let us test the exact model that we went in wanting to test. It also allowed us to create latent variables. It allowed us to estimate indirect paths, and doing SEM allowed us to run multi-group analyses. So we could see how stable that model was across random sample halves, across the 5 cultural groups, and across Buddhists and non-Buddhists. We had a reviewer who was really pushing us to try and make the best use of our data and strengthen our paper as much as possible. And so we augmented these SEM analyses with network analyses, which are exploratory rather than confirmatory. And we used 14 nodes. The nice thing about network analysis, in addition to being exploratory, it gives you centrality estimates, as I've already mentioned, so we can see which processes seem to be more centrally important. Our sample had 2,000 subjects and 14 nodes, so it was definitely a large sample. So we plan to do model selection with GGM model select. I think it's mod select. And then in BootNet, and then use MGM to get multiple R-squared estimates. So this is our SEM result, which has now, this paper just got accepted, thankfully, at mindfulness. So you can see our aspects of mindfulness are linked to greater present moment awareness, which is promoting decentering from difficult or challenging things, not immediately reacting to them, which promotes value-driven behavior, which is promotes well-being. In contrast, like taking a punishing karmic view or anatta are linked to slightly more distraction and inattention in day-to-day life, which promotes defensively reacting to difficult stimuli, more aimless haphazard behavior, and distress. And what was cool is not only did we get good fit in the whole sample for that, but we got excellent fit even when we constrained it to be identical across sample halves, across culture groups, and across Buddhist and non-Buddhist. So these tenets function in a similar way, and this cascade of sort of mindfulness processes seems to operate similarly across those different groups. But it was those are cross-sectional, and whether that's the exact order of the stages going from Buddhism to well-being is unclear. Also, our reviewer really didn't like that, if I go back a slide, that value-driven behavior was so far over, so late in the process. And he argued that in Buddhism, ethical value-driven behavior is far more integral, as is meditation. So we ran network analysis, and I'm going to show you the analysis first. So this is using one of those spiral graphs, a spring graph, where you graph it based on how central things are. And you can see we roughly got the stages, the forms of mindfulness predicting present moment awareness, predicting decentering and defensiveness, predicting value-driven behavior, and well-being. But what was nice and what made the reviewer happy is that ethical value-driven behavior is now super centrally located, as is meditation and mindfulness. And that's really consistent with Buddhist theory. We also, just to make this graph, to make a second graph that is more directly comparable to the SEM analyses we showed, you can specify where you want the nodes in your graph just by giving them coordinate locations on an arbitrary grid. And so I took these exact same results and graphed them more in line with how we were diagramming the model. And you can see in general, although there are a lot of edges in here, the strongest edges are pretty consistent with the direction, with the linkages we were proposing. Okay, so how did I do this network analysis? Usually any R code starts with a bunch of install packages things. R is pretty good. If you're trying to install bootnet and you need, there are like 3 or 4, I mean, you can put in this dependencies equals true so that if it needs another package, it pulls that package in as well. If you don't do that and you try to install the bootnet package and it needs 3 or 4 other packages, it will just tell you, by the way, you have to install these. Once they're installed, you then have to call them right before you, well, not right before, but in the same syntax that you're going to use them. And so to get the data in, I took the variables that were ready to be analyzed from SPSS, saved them as a CSV file, and then just used the reader package and use this read CSV command and had it pull in the data. It just like SPSS saves it, when it saves the CSV, it anticipates that the first row of data are the variable names. Then that data set had more variables than I wanted to analyze in a single analysis. So I took that data frame in the previous slide. I read that into this data frame or chunk of data, dat totals. Then I took dat totals and I used the dplyr package to just extract, I used the select function from that package to just extract a subset of the variables. So this would be the equivalent of use variables R in M+. And I actually renamed them. They had longer names for when I was running other analyses, but in the network, looking at the graphics, having more than 4 or 5 character names made it, the words so teeny tiny, it was super hard to see. So I just used this rename thing to give them each really short names. Then I pulled in the bootnet and QGraph libraries. And this is this net_ggm mod select. There's nothing magical about that name. That's just the data frame that's going to hold my results. This arrow is pushing the results into them. It's this estimate network function that is telling R what to do. I tell it what my data file is. It always expects the data file first. I said stepwise equals true. Missing equals pairwise. That's so it tries to retain as much data as possible. Default equals ggm mod select. That's telling it what strategy to select models with. And core method equals spearmint to deal with skew in my data. And to be honest, I can't remember off the top of my head. This was directly from Sasha's code that he gave in that class. I can't remember why we did stepwise equals true. That will give me the network that will give me the network. I can graph now. I can look at amounts of centrality for different variables. These few lines of code do all of that work. It does take, depending on how complicated how many nodes are in your model, this could take a while because GGM mod select does a pretty exhaustive search. But before I graphed it, I wanted to get capital R squareds. And for that, I was going to use the MGM package. Now I brought in Miss Forest, which is a data imputation package, and Huge, which is a data transformation package. I took my main data file, and for some reason, Miss Forest wasn't seeing it as a data frame. So I used this command to turn it into what Miss Forest would recognize as a data frame, and then ran Miss Forest on that and put it into dat impute. And oddly enough, the dat impute data frame seems to have both the unimputed data there and the imputed data there. If I want just the imputed data, then I have to say within this data frame, I use this $sign to say, show me just the imputed data, which is this ximp, and I put that into a data frame. And then for some reason that didn't, the huge thing wasn't recognizing that as a data frame. So I took that, turned it into a data frame, gave it a new name, dat by UFM model, NM for no missing, and then put that data frame into the huge.npn function, which gave me normalized data. Then I pulled in the MGM function, and that normalized data also wasn't recognized. It wasn't recognized as a matrix, so I had to use this as matrix function to create this. And then you need a variable P1, which is the number of columns in your, basically the number of variables in your analysis. So I used this to get that. I set a random seed to 1 so that if I did this again, it would give me the same results. And then I ran MGM. I said, this is my data, saying type equals rep quote G, and that comma with the number of nodes, tells it that it's Gaussian variables, that I want to do partial correlations. Level equals rep 1, comma, the number of nodes, tells it that it's continuous variables. And here, I don't have that GGM mod select, so I just used EBIC to extract it. Oh, that's better. And all of that got saved into fit object 1. Then I took fit object 1 and the data and asked for multiple R squareds with this predict function. And that gave me this, which basically tells me what proportion of variance is accounted for in each of my nodes. So to graph it, I did one more thing before I graphed it. I made a grouping scales data frame. I created a list, and I said the first batch of variables are the tenets of Buddhism, their variables 1 through 6. The next batch are mindful lenses, their variables 7 and 8. Flexible defensive responding, 9, 10. Ethical haphazard behavior, 11, 12. And individual function, 13 and 14. So this is your graph. And so I'm saying graph This is my results data frame, net underscore ggm mod select. I'm putting a $sign in and saying, give me just the graph from that. But then I'm giving it a whole bunch of commands. I want it to be a spring. This pi command is what puts what puts the ring around each node that is filled to the degree that that variable was explained by other variables. So putting this predict object one $sign error in fills that in. And I just told it to have a hot pink color. And then I wanted the nodes to be labeled. I could have used any of my data frames. I don't know why I used this normalized one, but any of them that have those appropriate 4-letter labels would work. I told it to show the labels to this with the same font size. I didn't want a legend because the legends it creates look like crap and I couldn't make them look good in R. So I decided for my figures, I would just create them myself. And then I said groups equals that data frame I made. And then the colors of the nodes for those groups I entered here in hex code. And that gave me this output, which I have already shown you. How are we doing on time? We're doing okay. Now I told you, I wanted, this isn't exact. I couldn't find the one that I used to create the UFM one, but you can put your variables on any grid and then decide where you'd like them to be, and then create another vector, a matrix that has, if you have 14 nodes, 14 pairs of coordinates, one for each node in order. And so you can get another graph. So instead of saying layout equals spring, you say layout equals that vector. And then everything else is about the same. And then you get this because you've now specified exactly where you want those nodes to fall. And I thought personally, it was most informative seeing both of them. The spring graph where they were placed based on their centrality, and then this graph where they're placed based on the model that I was hoping to test. And you can see these little hot pink things are showing you how much variance is accounted for in each of those nodes. Now, especially if you're doing this in a smaller data set, but even if you're doing it in a larger data set, it's important with network analysis to evaluate how stable your network is. How stable are these findings? How much confidence should we have in them? And they've actually built a bunch of ways of doing that in these packages, super easy. So there's really no excuse not running these analyses. First, they have a whole simulation package to help you estimate power. It helps you estimate sensitivity. How much power do you have to detect true edges? Specificity, how much power do you have to successfully not include edges that shouldn't be there? And correlation, it looks at I think it's doing, for this, it's doing bootstrapped analyses, and it's looking how much the estimated edge weights and all of those sample match the true edge weights. So that all happens with the net simulator function. This is directly out of the Sasha's paper, but I'm going to show you it here. So I ran net simulator. I put my graph in, the same one that I graphed in those previous codes, as the model that we should be getting. And then I told it a bunch of sample sizes to estimate these things for. I asked it to do 100 repetitions of each of these sample sizes. and that it should use the GGM mod select, because that's what I had used. Stepwise equals true again, and the core method spearmint. And when I plot those sims, I get these plots. So even if I had dropped down to a sample of just 400, the estimated edge weights would correlate about 0.90, 0.91 with actual edge weights. So that's really good. But with my sample of 2091, they correlate close to 0.98, 7.98. So a very stable edge weights, which is nice. This is sensitivity. So this is my power to detect the edge weights that I believe are real. I have about a median power of about 90%, 90%, which is good. And even the full distribution of that doesn't go down below 0.8. And specificity is even better. My ability to accurately detect edges as not significant was pretty darn close to 1. So in addition to looking at power, there are 2 more things that you can quite easily do with the BootNat package. You can look at confidence intervals for the edges. So you do BootNet and you bring in your results, you tell it how many bootstraps to do, split 0 equals true, and n res equals 6. And when you plot it, you get this nice plot. Now with 2,000 participants, these light gray confidence intervals are fairly tight. So some of these strongest edges are definitely statistically significantly different than these weaker ones. And there are probably even differences, even more differences. In fact, you can get another plot I didn't show you that tells you which edge weights are significantly different from which others. You can also look at the centrality. I told you that ethical value-driven behavior was very central, and it came out as about the most central construct across all 3 indices of centrality. And I got this, you can get these numbers just by doing this command. You can get these plots by doing this command. You can look at the stability of those central indices. And you do that by case dropping bootstrapping. So this is like, if I drop 10% of the sample. So I'm bootstrapping, but I'm bootstrapping down to 90% of my original sample. How stable are these different centrality indices? And you can see they're pretty stable. And this is how much the bootstrap things correlate with the actual, with the results in the original sample. And you can see they correlate really high with my sample, even all the way up to dropping 80, or I'm sorry, dropping 20 or 30% of my sample. You want these correlations to be above 0.5. So this is telling me I have a pretty stable estimates of centrality. And then I just thought I would show how I wrote this up. This is the analytic strategy prose that I used. I explained what we were running it on. And I explained why we use the model selection and gave all of the citations. And then I gave sample results prose from this paper. So the teal color is explaining the graphs that are in the results. The blue is actually describing the results. The pink is talking about centrality, since that was really new from this analysis. I also had some suppressor effects come out. I was very hesitant about interpreting them, especially because some of the suppressor effects came out for not self, anatta, like seeing yourself, the idea of self as a fallacy and something to be let go. That's probably hard for us to measure in a self-report survey, especially with people who aren't studying Buddhism. So anyway, some Buddhists see that as super critical for achieving the highest levels of mindfulness. And so it was particularly concerning to my Buddhist monk colleague who was on this paper with me that not self was coming out with these odd results. So we were very hesitant. You can see in our the purple sentences about interpreting those. And then this is the final paragraph where I talk about the stability of the model. So that in 55 minutes is how to run network analysis. Any questions? Well, it shouldn't be too hard. They're like, I know that there's a lot of steps, but I think I tried to make these, we'll put these slides on the HSDG thing. And I can even put the Buddhism paper up there as a nice example.
Can you put your brain up there for us to use?
What?
Can you put your brain up on the website for us?
It's not that it, I mean, there are a few decision points, mostly around, do you have a big sample or a large sample? So should you do lasso regularization or model selection? But a lot of this code, I mean, and I know it might look a little intimidating because I went through the learning curve. Well, I went through the learning curve and it's like, okay, I'm supposed to be able to use this function, but I keep getting this error. This is not a matrix. So I had to figure out the as matrix command to make it, to force it to use that. But if you use this code as a template with, I would say if a grad student watched this video and read Sasha's paper, then with a half hour of time, we could edit the code and have it work in their data. So it's
I think that's why it's so great to record this now, because like, you know, I see myself like, okay, I can go back and watch this recording again. So
I mean, I kind of think of this network analysis as sort of an exploratory path analysis, which makes it kind of cool. And if it I mean, it didn't perfectly fit our model, but it came kind of close. So it was a nice sort of affirmation of what we were putting next to each other, which I thought was kind of cool.
Do you think, Ron, I know, sorry, oops. Do you think, I know in the psychopathology literature, people use network analysis a lot, but there's a lot of criticism of it. And I am not totally up on all of what the criticisms are, but I think a lot of it boils down to that it's basically correlations, right? Like it's basically a lot of it, especially if you're using cross-sectional data, which a lot of it is. So is it getting, or is that essentially what you're doing? Like you're essentially like doing really fancy correlation, or are there other criticisms that when you were reading about this that you came up with? So I know that
some of the criticisms are, those were earlier. Some of the criticisms were about stability. But I think if you do those final analyses and you show that you have a stable solution, that you can trust the centrality estimates, that you can trust the edge weights, that you've addressed that. And so that's less of a concern. But if you're trying to do a lot of nodes in a, in 100 undergrads or something like that, reviewers could say, I'm not sure I trust these results. I want you to do, it seems like you need a more diverse and much bigger data set. And that, were you to try to submit that to a journal with an impact factor of 3 or higher, it probably would get rejected if you had a really tiny sample. Does that make sense? So part of it is stability, part of it, but you're right, it is the same as running path analysis in cross-sectional data. Exactly the same. I mean, you're going in and parsing out that correlation matrix. You're just doing it in a slightly different way and in more of an exploratory way. But it has all of those limitations. So if a journal is predisposed to never publish cross-sectional data, they're not going to be happy with your cross-sectional network analysis. Now you can do longitudinal network analysis, although I have not seen that many of those in the published literature. But that's the MGM package is trying to make it so it's easier for you to take multi-wave data and run the network analysis in it.
Or diary data.
Yeah.
You may.
So obviously, if you have longitudinal data, then that's less of a concern. Although if you have longitudinal data, if you have diary data, you could just run you could run the analyses in SEM, either with a random intercepts cross-lag pattern model or with multi-level modeling, right?
Yeah, I mean,
Just like you can run, just like with cross-sectional data, you could run SEM analyses instead of running network analyses.
I mean, like with the psychopathology models, it's sort of like people make the argument that they do it to test a totally different kind of model than you would in SEM. In SEM, you're trying to be like, there's a latent variable, like an internalizing factor, for example, that's accounting for all these symptoms.
Right. Mm-hmm.
Network analysis, the idea is that this symptom leads to this symptom versus like this symptom, like that there's this
right, exactly.
patterns. So like it's something that's totally different than you would use with SEM.
Although with the yes, and if you have a set of symptoms that would normally form a latent variable in an SEM structural model, those symptoms might form a really tight cluster in network analysis. Does it make sense?
Yeah.
But then you would be able to see which of those symptoms are uniquely linked to other things. Mm-hmm. So you're modeling the covariance among them, but you're also seeing the unique variance of each of them. You know how like in your models, sometimes you'll have these observed variables, you'll make a latent variable, and you kind of want to see, well, we did that with it's like in that Buddhism model, we had those 6 tenets of Buddhism. Putting them in that way as the exogenous variables, all of their shared variance got thrown out. And it's really that shared variance that is truly Buddhism, right? And we kicked all of that out of the model. We had another model where we made a latent variable, and the reviewers were like, why do you have another model? And we had explained really clearly that we wanted to model the shared variance and the unique variance. Well, in network analysis, you're doing both at the same time, kind of. Anyway, Sasha Eskamp is with this psychometric package is trying to make it so you can, like when we did the network analyses for those latent variables, we just made composites. When we did the network analysis, because we didn't want to throw 30 things into the network analysis. We wanted to keep it nice and simple. But Sasha Eskamp is making, allegedly, I couldn't find the code for it, but allegedly right now with psychometrics, you can create latent variables and then run network analysis on those latent variables.
Cool.
Okay, well, I think, is any more questions?
I just have one question. With the with the whole diagram thing with your Buddhist variables, the 6 of them, they showed up on the left-hand side of your network analysis, kind of like how you specified it in the SEM. Did it do that automatically, saying that maybe these are the exogenous variables, or did you do that?
I didn't. It did that automatically. I don't. And I mean, I would imagine that left to right is arbitrary. Like literally, it just came out like that. I was super lucky. But had it been sort of rotated 180 degrees, we could have rotated it back 180 degrees, because the result is the thickness of those little bars and stuff. It's not, or am I looking at it like this or like this? Does that make sense? But they just happened to, I mean, I'm wondering if they came out on the left-hand side because they were some of the first variables in the data frame. I don't know. But it was completely arbitrary, and we didn't specify it in that spring graph.
So it's not necessarily saying that those are the main predictors and everything else follows after it or anything.
Well, with network analysis, you're assuming everything predicts everything. And you're kind of assuming, a lot of these paths are going to probably be bidirectional, right? We don't know what direction they are. So we're just saying, don't put any arrowheads in whatsoever. Just draw a line to show that they're linked. Does that help?
Yeah, thank you.
All right, well, thanks, Ron.
Have a great weekend.
Go enjoy the weather.